Hello sir, I am Shreya Swami. I am here to give a presentation on the topic ECOS and TINYOS. So what is ECOS? It is a embedded configurable operating system. It is an open source loyalty free and real-time OS intended for the embedded application. It is mainly targeted at the high performance small embedded systems. For such systems, an embedded form of Linux or other commercial OS would not provide the streamlined software as required. So the ECOS software has been implemented on a wide variety of processor platforms like Intel IA32, PowerPC, Spark, ARM and etc. Next, let us see the ECOS configurability. An embedded OS that is flexible enough to be used in a wide variety of embedded applications and on a wide variety of embedded platforms must provide more functionality than will be needed for any particular application and the platforms. For example, we can take many real-time operating systems support task switching, concurrency controls and a variety of priority scheduling mechanisms. A relatively simple embedded system would not need all the features. So the challenge is to provide an efficient user-friendly mechanism for configuring selected components and for enabling and disabling particular features within components. The ECOS configuration tool, which runs on a Windows or Linux, is used to configure an ECOS package to run on a target embedded system. The complete ECOS package is structured hierarchically, making it easy using the configuration tool. So, using the configuration tool to assemble a target configuration. At the top level, ECOS consists of a number of components and the configuration user may select only those components needed for the target application. We can take an example. A system might have a particular serial I/O device. The configuration user would select serial input output for this configuration. Then select one or more specific input output devices to be supported. The configuration tool would include the minimum necessary software for the support. The configuration user can also select specific parameters such as the default data rate and the size of the input output buffers to be used. So next, let us see the components of the ECOS. These are the components of the ECOS. It is a user application code, standard C library, I/O system, also known as device drivers, kernel and hardware abstraction layer. So let us see the first hardware abstraction layer. It is also known as HAL. It is at the bottom in the architecture. So the HAL is the software that presents a consistent API to the upper layers and maps upper layer operations onto a specific hardware platforms. So the HAL is different for each hardware platform. Each hardware platforms. Okay. Next, there are separate modules in the HAL, that is architecture, variant and the platform. So what is architecture? It defines the processor family type. It contains the code necessary for processor startup, interrupt delivery, context switching and other functionality specific to the instruction set architecture of the processor family. Next module is a variant. It supports the features of the specific processor in the family. For example of supported feature is an on-chip module such as memory management unit, that is MMU. Next module is the platform. It extends the HAL support to tightly coupled peripherals like interrupt controllers and the timer devices. It also defines the platform or the board that includes a selected processor architecture and variant. It includes codes for startup, chip selection configuration and interrupt controllers and timer devices. So let us see the next component of the ECOS, that is the ECOS kernel. The ECOS kernel is mainly designed to satisfy the following objectives, that is the low interrupt latency, low task switching latency, small memory footprint, and deterministic behavior. So, what is low interrupt latency? In this, the time it takes to respond to an interrupt and begin executing the ISR. ISR is interrupt service routine. So, next objective is low task switching latency. It is the time it takes from when a thread becomes available to when actual execution begins. Next is a small memory footprint. It is a memory resource for both program and data that are kept to a minimum by allowing all components to configure memory as needed. So next is a deterministic behavior. Throughout all aspect of execution, the kernel performance must be predictable and bounds to meet real-time application requirements. Next component is the ECOS IO system. So, ECOS IO system is a system of framework for supporting device drivers. A variety of drivers for a variety of platforms are provided in the ECOS configuration package. These include the drivers for serial devices, Ethernet, flash memory interfaces, and the various IO connects such as PCI, USB, and etc. Here, users can also develop their own device drivers. The principal objective for the IO system is efficiency with no unnecessary software layering or the extra functionality. Here, device drivers provide the necessary functions for input-output buffering and the device control. The kernel also provides a 3-level interrupt model, that is interrupt service routines, deferred service routines, and the threads. So, interrupt service routine, it is also known as ISR. It is invoked in response to the hardware interrupt. Hardware interrupts are delivered with minimum of interventions to an ISR. The HAL decodes the hardware source of the interrupt and calls the ISR of the attached interrupt object. Here, the ISR may manipulate the hardware but is only allowed to make a restricted set of calls on the driver API. Next is a deferred service routines. It is invoked in a response to a request by an ISR. Here, the DSR will run when it is safe and without any interfering with the scheduler. Most of the time, the DSR will run immediately after the ISR, but if there is any current thread in the scheduler, then it will be waiting until the thread is completed. A DSR is allowed to make a larger set of driver API calls, including the call CYG DRV condition signal to wake up the threads. Next is the threads. The clients of the driver. Threads are able to make all API calls and in particular are allowed to wait on mutexes and conditional variables. Next is a ECOS scheduler. So the ECOS kernel can be configured to provide one of two scheduler designs, that is the bitmap scheduler and the multi-queue scheduler. Let us see in detail. A bitmap scheduler supports multiple priority levels, but only one thread can exist at each priority level at any given time. Scheduling decisions are quite simple with the scheduler. So this is the bitmap scheduler priority level. In this, when a block thread becomes ready to run, it may preempt a thread of lower priority. When a running thread suspends, the ready thread with the highest priority is dispatched. Here, a thread can be suspended because it is blocked on a synchronized primitive, because it is interrupted, or because it loses the control. As there is only one thread at each priority level, the scheduler does not have to make a decision as to which thread at a given priority level should be dispatched next. The bitmap scheduler is configured with 8 or 16 or the 32 priority levels. A priority bitmap is kept of the threads that are ready to execute. This need only determine the position of the most significant one bit in the bitmap to make a decision. Next is the multi-level queue scheduler priority. This is the architecture showing this priority. Okay. And as in the bitmap scheduler, the multi-level queue scheduler supports up to 32 priority levels. The multi-level queue scheduler allows for multiple active threads at each priority level, limited only by the system resources. Here, a data structure represents the number of ready threads at each priority level. When the blocked thread becomes ready to run, it may preempt a thread of lower priority. As with the bitmap scheduler, a running thread may be blocked on a synchronization primitive because it is interrupted or because it loses the control. When a thread is blocked, the scheduler must first determine if one or more threads at the same priority level as the blocked thread is ready. If so, the scheduler chooses the one at the front of the queue. Otherwise, the scheduler looks for the next highest priority level with one or more ready threads and dispatches one of these threads. Here, the multi-level queue scheduler can be configured for time slicing. Thus, if a thread is running and there is one or more ready threads at the same priority level, the scheduler will suspend the running thread after one time slice and choose the next thread in the queue at that priority level. This is a round-robin policy with one priority level. Next is the ECOS thread synchronization. The ECOS kernel can be configured to include one or more of 6 different thread synchronization mechanisms. Those includes classic mechanism, synchronization communication mechanisms, or the SMP support, that is symmetric multiprocessing. Let us see in detail. The first one is the mutexes. The mutex is used to enforce mutually exclusive access to a resource, allowing only one thread at a time to gain the access. The mutex has only two states, that is locked and other is unlocked. It is similar to a binary semaphore. When a mutex is locked by one thread, any other thread attempting to lock the mutex will be blocked. When the mutex is unlocked, then one of the threads blocked on this mutex will be unblocked and allowed to lock the mutex and gain access to the resource. Here, the mutex differs from a binary semaphore in two ways. The first one is the thread that locks the mutex must be the one to unlock it, or it is possible for one thread to lock a binary semaphore and for another to unlock it. The other difference is that a mutex provides protection against priority inversion, whereas a semaphore does not give protection. Next, let us see what are semaphores. So, the ECOS kernel provides support for a counting semaphore. Counting semaphore is an integer value used for signaling among the threads. The command cyg_semaphore_post command increments the semaphore count. If the new count is less than or equal to the 0, then the thread will be waiting on the semaphore and until it is awakened. The next command cyg_semaphore_wait checks the value of semaphore count. If the count is 0, then the thread calling this function will wait for the semaphore. If the count is non-zero, then the count is decremented and the thread continues. Counting semaphores are suited to enable threads to wait until an event has occurred. The event may be generated by a producer thread or by a DSR in response to a hardware interrupt. Then another use of a semaphore is for the forms of resource management. Here the counter would correspond to how many of a certain type of resource are currently available, with threads awaiting on the semaphore to claim a resource and posting to release the resource. And next is a condition variables. A condition variable is used to block a thread. until a particular condition is true. Condition variables are used with mutexes to allow multiple threads to access shared data. In equals condition variable, these are typically used in conjunction with mutexes to implement long-term waits for some condition to become true. Next is the event flags. Event flag is a 32-bit word used as a synchronization mechanism. It is an application code may associate a different event with each bit in a flag. A thread can wait for either a single event or a combination of events by checking one or multiple bits in the corresponding flag. The thread is blocked until all of the required bits are set, or until at least one of the bits are set. A signaling thread can set or reset bits based on specific conditions or events so that the appropriate thread is unblocked. For example, bit 0 could represent completion of a specific IO operation, making data available, and bit 1 could indicate that the user has pressed a start button. A producer thread or DSR could set these two bits, and a consumer thread waiting on these two events will be broken up. Next is mailboxes. Mailboxes can also be called as message boxes. These are ECOS synchronization mechanism that provide means for two threads to exchange information. The ECOS mailbox mechanism can be configured for blocking or non-blocking on both the send and receive side. The maximum size of the message queue associated with the given mailbox can also be configured. Next is the spin locks. A spin lock is a flag that a thread can check before executing a particular piece of code. The basic operation of the spin lock is only one thread at a time can acquire a spin lock. Any other thread attempting to acquire the same lock will keep trying until it can acquire the lock. A spin lock is built on an integer location in memory that is checked by each thread before it enters its critical section. If the value is 0, the thread sets the value to 1 and enters its critical section. If the value is non-zero, the thread continually checks the value until it becomes 0. Next, let us see the another OS, that is a TINYOS. The ecosystem provides a more streamlined approach for an embedded OS than one based on a general purpose OS, such as the embedded version of Linux. The ecos and similar systems are better suited for small embedded systems with tight requirements on memory, processing time, real-time response, power consumptions, and etc. TinyOS takes the process of streamlining to a much further point, resulting in a very minimum OS for embedded systems. The OS requires only 400 bytes of code and data memory are combined. TinyOS represents a significant departure from other embedded operating systems. The difference is that TinyOS is not a real-time OS. The reason is that for this is the expected workload which is in the context of wireless sensor network as described in the next subsection. Because of power consumption, these devices will be halved most of the time. Here the applications will be simple with processor contention, not much as an issue. In TinyOS, there is no kernel as there is no memory protection and it is a component based OS. So there are no processors and the OS itself does not have the memory allocation system. Interrupt and exception handling is dependent on the peripheral and it is completely non-blocking, so there are few explicit synchronization primitives. TinyOS has become a popular approach to implementing wireless sensor network software. Currently, over 500 organizations are developing and contributing to an open source standard for TinyOS. Let us see the wireless sensor networks. This is the wireless sensor network topology. TinyOS was developed primarily for use with networks of small wireless sensors. Uh, it has enabled the development of extremely compact low power sensors. Smaller size in turn reduces power consumption. Low power and small size trends are also evident in wireless communications hardware, electromechanical sensors, that is MEMS. It is possible to develop an entire sensor complete with logic in a cubic millimeter. This architecture shows a typical configuration. It has a base station connecting to a sensor network, that is host PC, and passes on a sensor data from the network to the host PC, which can do data analysis or transmit the data over a corporate network as it is shown here, or internet to a analysis servers. Individual sensors collect data and transmit these to the base station either directly or through sensors that acts as a data relays. The mobility of individual sensors and the presence of RF interference means that the network will have to be capable of reconfiguring itself in a matter of seconds. There are some goals of TinyOS. With a distributed sensor application in mind, these goals were created. The first goal was high concurrency. In a typical wireless sensor network application, the devices are concurrency intensive. Several different flows of data must be kept moving simultaneously. While the sensor data is input in a steady stream, processed results must be transmitted in a steady stream. In addition, external controls from remote sensors or base stations must be managed. Next goal is operate with limited resources. The target platform for TinyOS will have limited memory and computational resources, and it runs on batteries or solar power. A simple platform may offer only kilobytes of program memory and hundreds of bytes of RAM. The software must make efficient use of the available processor and memory resources while enabling low power communication. Next goal is adapt to hardware evolution. Here, hardware is in constant evolution. Applications and most system services must be portable across hardware generations. So, it should be possible to upgrade the hardware with little or no software change if the functionality is same. Next goal is support a wide range of applications. Applications exhibit a wide range of requirements in terms of lifetime, communication or sensing or etc. A general purpose embedded operating system is designed so that a standardized approach leads to economies of scale in developing applications and support software. Next goal is support a diverse set of platforms. General purpose embedded OS is desirable. And next goal is be robust. Once deployed, a sensor network must run unattended for months or years. Ideally, there should be redundancy both within a single system and across the network of sensors. However, both types of redundancy require additional resources. One software characteristic that can improve robustness is to use high modular standardized software components. So, the components of TinyOS. An embedded software system built using TinyOS consists of a set of small modules called the components, in which each of them performs a simple task or a set of tasks, and which interface with each other and with hardware in a limited way. The only software module is the scheduler, because there is no kernel, there is no actual OS. But we can take the application area of interest is the wireless sensor network. To meet the demanding software requirements of the application, a rigid simplified software architecture is dictated, consisting of the components and different components. The TinyOS development community has implemented a number of open source components that provide the basic functions needed for the WSN applications. Examples of such standardized components include single hop networking, ad hoc routing, power management timers, and non-volatile storage control. For specific configuration and applications, users build additional special purpose components and link and load all the components to the application. Here, the TinyOS then consists of a suite of standardized components. It consists of some, but not all the components. So, the OS for the implementation is simply the set of standardized components from the TinyOS root. All components in a TinyOS have the same structure. Next is the TinyOS scheduler. So, the TinyOS scheduler operates across all the components. Virtually all embedded systems using TinyOS will be uniprocessor system, so that only one task one task among all the components may execute at a time. The default scheduler in TinyOS is simple FIFO, that is first in first out queue. The task is posted to the scheduler either as a result of an event which triggers the posting, or as a result of a specific request by a running task to schedule another task. Here the scheduler is aware of power. It means that the scheduler puts the processor to sleep when there are no tasks in the queue. The remaining operating systems should or can wake up the system by means of a hardware event signaled to a lowest level component. Once the queue is empty, another task can be scheduled only as a result of a direct hardware event. This battery enables the efficient usage of the battery. So the scheduler has gone through two generations. That is in TinyOS 1.x. That is, there is a shared task queue for all tasks, and a component can post a task to the scheduler any number of times. If the task queue is full, the post operation fails. Experiencing with networking stacks showed this to be a problematic, as a task might signal completion of a split phase operation. If the post fails, the component might block forever, awaiting for the completion event. The another generation is TinyOS 2.x. Every task has its own reserved slot in the task queue, and a task can only be posted once. A post fails if and only if the task has already been posted. If a component needs to post a task multiple times, this slight change in semantics greatly simplifies a lot of component code. So, rather than test to see if a task is posted already before posting it, a component can just post the task. Components do not have to try to recover from failed post or and then retry. The cost is 1 byte of a state per task. There are some resource interfaces in TinyOS. Those are dedicated, virtualized, and shared. Let us see in detail. TinyOS provides a simple but powerful set of conventions for dealing with the resources. So the first resource is dedicated. It is a resource that a subsystem needs exclusive access to all the times. In this resource, there is no sharing policy needed, and because only one single component ever requires use of resources. Example of this is interrupts and the counters. And next resource is a virtualized resource. Here every client of a virtualized resource interacts with it as if it were a dedicated resource, with all virtualized instances being multiplexed on top of a single underlying resource. The virtualized abstraction may be used when the underlying resource need not be protected by mutual exclusion. The example includes clock or the timer. And next resource is the shared resource. The shared resource abstraction provides access to a dedicated resource through an arbiter component. The arbiter enforces mutual exclusion, allowing only one user, that is the client, at a time to have access to a resource and enabling the client to lock. Here, the arbiter determines which client has access to the resource at which time. While a client holds a resource, it has complete and unfettered control. Arbiters assume that clients are cooperative, only acquiring the resource when needed and holding onto it no longer than necessary. Clients explicitly releases the resources. Thank you.